Everybody. My name is Tanya Reinhardt, and on behalf of the University of KwaZulu-Natal, I would very much welcome you to our public online lecture series, What Do Scientists Do? A look inside the ivory tower in celebration of National Science Week. If I can just ask for some housekeeping things, please make sure that you have muted your microphone. So in order to find the mute button, you just move your mouse pointer to the bottom left, and on the left-hand side, there's a microphone, and it needs to have a red line across. Also, because we are having issues, some of us having issues with bandwidth, if you can please leave off your camera, that would be very much appreciated. We will also have a short question and answer session after the talk. Unfortunately, Professor Brooks has limited time, but you can post the questions in the chat or in the Q&A section. Okay, so we're ready to rock and roll, and I just wanted to give you a brief background on National Science Week. So this is an annual event aiming to exhibit and communicate awareness in science, and it is an initiative of the Department of Science and Innovation, DSI. The countrywide celebration of science involves various stakeholders, so for example, us as university and role players who run science-based activities during the week. The event is implemented by the South African Agency for Science and Technology Advancement, NRF-SASTA, and has an overall theme. And for this year, making it possible through science. And Mike would probably agree, a better title would actually be making it possible through science and engineering. Our speaker, and it gives me a really a great pleasure to introduce to you our guest speaker for this evening. Professor Mike Brooks is an associate professor and head of mechanical engineering at the University of KwaZulu-Natal. He's the co-founder of the UKZN Aerospace System Research Group, and I'll just leave the abbreviations out. A senior member of the American Institute of Aeronautics and Astronautics, and the program manager of the ASREG Phoenix Hybrid Rocket program. This program focuses on space propulsion research in hybrid and liquid rocket system. And today he's going to present a very exciting talk with the title #WeFlyRockets, the why and the how of aerospace propulsion research at UKZN. Mike, I'm gonna leave you the floor.
Thank you, Tanya, and good afternoon, good evening, everybody. It's a pleasure to be here for this National Science Week presentation on rockets. And it's a pleasure to do this. I'm going to share my screen and we'll get the presentation underway. For the sake of bandwidth, I'm going to switch my video off and let's get going. Well, I hope you can all see the slides. I'm sure Tanya will let me know if anything is untoward. I apologize in advance if the bandwidth makes things a little bit grainy. We'll do our best to get through this with the clearest possible presentation. So yeah, this is a presentation on the why and the how of UKZN's Aerospace Propulsion Research Program. It's quite a mouthful, so maybe we could just call it We Fly Rockets. And before I begin, I want to acknowledge my colleagues in mechanical engineering, Dr. Jean Peteau, who's the leader of ASREG, the Aerospace Systems Research Group, Professor Glenn Snedden, Mr. Timothy Veldhuizen, and all of the students who have contributed to this presentation. So what we're going to look at this evening is, first of all, why are we doing this research? Everything we do, all the research that is done at the university needs a reason, and we're going to look at that reason to begin with and the context of the work that we do. I will then look a little bit at the Aerospace Systems Research Group, which is what we call ASREG, the pronunciation there, ASREG. And then we will move on to the how of rocket design and manufacture. So I'm sure that some of you are interested in what actually goes into the process of designing a rocket. Then we will look at the fun part. I think it's the fun part because most people are really interested in seeing these things fly or not. And we will go through this section, and I've titled this How Things Go Right and Wrong, and you'll see what I mean a little bit later on. And then we'll wrap things up a little bit down the line. So why are we doing this work? So in order to answer this question, I want to take a quick dive back into history and just point out that as many of you will know, I think many of you will be aware that there was previously something called the space race. And the space race was between the superpowers, the Soviet Union and the United States. And this really began after the Second World War, 1945. At the end of the war, of course, the country that had the most advanced rocket program was Germany. So in the years immediately after that, those German scientists, a lot of them found their ways either to the Soviet Union or to the United States and started the rocketry programs in those countries. And what followed was what we now call a kind of old space race. And that was a space race to conquer space. And it was done largely by governments. It was government funded. It was geopolitically driven. These were big flag waving exercises to get the first man into space, to get the first man on the moon. And of course, they were heavily military oriented. So there were almost all of the initial rockets, in fact, all of the rockets that we now know originated in the early 50s and 60s at least, originated with military backgrounds. They were missile programs. So, but they did turn slowly into commercial vehicles, and one of the characteristics was they were massively expensive. So you had to fork out huge amounts of money to buy one of these rockets. They were pioneering, but they were primitive technology. And importantly, they were out of reach of smaller nations, and they certainly were out of reach of companies and private individuals. And there's a photograph of the American President Kennedy with Werner von Braun, who was the German scientist who is largely considered to be the father of the US space program. But then something happened. In the early 2000s, there was the new space phenomenon, which was born, and this was characterized by the entry of low-cost entrepreneurial launch providers. So we have the likes of SpaceX, and you can see a photograph there of the founder of SpaceX, the owner, Elon Musk, shaking the hands of Charles Bolden, the head of NASA. We have companies like Blue Origin, Virgin Orbit, Rocket Lab, Virgin Galactic. These are companies that are now taking over from where the governments used to do the development work. They are low cost. They operate in an agile manner. They are reliant on private capital very often, although also contracts, government contracts to some extent. They exploit new research and development models, and they embrace disruptive technology. And they like to reuse stuff. So here's a picture of a Falcon Heavy, which is a very large rocket. This is a SpaceX rocket. It's a beast. This can put about 60 tons of payload into low Earth orbit. And of course, that rocket has 27 engines on the booster stage, and each of those engines costs somewhere between $1 million and $2 million. So you really don't want to throw that away. Elon Musk has said that throwing rockets away is a little bit like, imagine getting on a commercial airliner flying from Johannesburg to Cape Town, and when you get off the plane, they take the plane and they trash it at the end of the runway and give you a brand new one when you fly home again. This is crazy. We want to reuse these things, and that's one of the features of the new space phenomenon. So, and they're not the only ones. There's a picture of Rocket Lab CEO Peter Beck, and he's holding one of the engines on the back, from the back end of the Electron rocket. And that's a full-size rocket. That's how big it is. So rockets are not only enormous, they can also be smaller, and that's important because the new space race is largely being driven to some extent by these small sat launch vehicles like Electron. And of course, there are other players in the game as well. There's Launcher 1 being launched from underneath a Boeing 747. There are other companies, Astra, Firefly, and all sorts of other companies. Now, I'm going to show you a little bit of video footage, if I can make this work. just to illustrate how reusability is coming along. And this is really important because it makes a huge difference to the costing model. So what I've got here is I've got a little bit of video. It's from YouTube, it's public video, and this is the launch of that Falcon Heavy rocket that you saw a little bit earlier. And I'm going to see if I can play this for you.
15 seconds.
Vehicle's flight pressures.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition, liftoff.
Vehicle is pushing downrange.
And we're beginning deep throttle.
Now, I've paused the video there because I want to point something out to you. Here is the vehicle in flight, and I don't know if you can see my cursor. I hope you can, but you'll notice that there are 3 cores. There are 3 Falcon 9 cores here. Obviously, there's a second stage up at the top of the rocket, but each of those 3 cores is very valuable. They want to bring them back. So what they're going to do, and I'm going to show you the video shortly, is you're going to see these 2 side cores departing the vehicle. They're going to leave the vehicle, they're going to flip themselves around, they're going to refire their engines, and they're going to head back and land themselves where they took off from at Cape Canaveral. Right, this is audacious stuff. So let's see if we can watch the side boosters departing the vehicle. Just keep your eye on the left and the right panels. So these are cameras on board the rocket, and you're going to see the left and right boosters departing.
Pedro.
Booster separation confirmed.
Successful separation, if you can hear me over the cheering. Side boosters now beginning a flip to begin returning back to Cape Canaveral.
Right, so we've got the boosters have left. The 3 bottom panels you see there, the one on the left is the camera on the left booster, the one on the right is the camera on the right booster, and the camera in the middle is on the central core. Now, what I'm going to show you now is I'm going to show you the landing. So remember, this is all about reusability. So let's go and see what these things look like when they come back down to Earth.
If we have a successful landing today, the side boosters will be reflown on our next Falcon Heavy mission, STP-2. Now, coming up at about T plus 6 minutes will be the side boosters re-entry burn.
Acquisition of signal Bermuda.
So you'll see the side boosters on your left and right screen.
Side booster entry burn has started.
And there's the re-entry burn beginning.
Stage 2 trajectory nominal.
And the re-entry burn is complete for the side boosters. Now, coming up in about 30 seconds, the center core, which you see on your center screen, will begin its re-entry burn.
Stage 1 entry burn has started. Side boosters are transonic.
And there you can see the re-entry burn for center core has begun. Coming up in about 5 seconds here, the side boosters landing burn will begin as well.
Side booster landing burn has started.
See the side boosters
Pushing.
You can hear our crowd going crazy right now. Both side boosters has landed on our landing pads. Zone 1 and Zone 2.
Okay, so you all, I think, appreciate that that's pretty audacious stuff. So that's at least 18 of those engines came back home again. The third booster, unfortunately, didn't land correctly out in the ocean, so they lost that. But you can imagine 18 engines recovered. So let's take another quick look at that, and I want to show you the view from the ground now, where the vehicle is photographed, or there's camera footage coming from the ground itself. And I want you to watch the top right-hand panel of this screen to see what is going on. Now you have to relight the engines on this thing. So it's quite impressive.
Center core entry burn shutdown.
And even though those look very similar, those two boosters views, those are actually representing different boosters. And they're heading towards Earth. They're about to begin their landing burns. We'll hopefully be able to bring you nice footage of that.
Both side boosters transonic.
And watch for the landing lights deploy at the tail end of that landing burn.
And that landing burn has started.
Both boosters looking to be on track towards their respective landing zones.
Landing legs have started. Side boosters landing legs have deployed.
And the Falcons have landed.
Right, so let me just get back to my presentation here for a second. Okay, so the message there is we need to be able to reuse these spacecraft, these rockets, because that is what gets us into the market. So let's do a little bit of the financial stuff now and understand what's going on with the market. So the graph that you see on the screen there is the number of annual small satellite launches. And this is forecast by a consulting group called Frost & Sullivan. So the market is, first of all, the global small sat. These are satellites under about 500 kilograms in mass. So they're very small. That's a small satellite, all the way down to CubeSats, which are about 1 or 2 kilograms in mass. And that market is projected to grow to about $18.3 billion by the year 2026. There's been a 27-fold increase in the number of investors getting into the development of launch vehicles because of this. And of the 2,500 satellites that were launched in the last between 2012 and 2019, 1,700 of those were small sats. So the bottom line here, and this graph shows you the potential revenues projected into 2030 for the small sat launch market. And you can see that it runs into the billions of US dollars. So what we know from this, or what we understand, is that the small space, the new space small satellite launch market is exploding. It's just mushrooming incredibly quickly. And that, in a nutshell, is the reason that ASREG is doing the work that it does, because we have commercial ambitions. But you have to start somewhere, you have to start small, you have to start to understand these very complex machines, and you have to develop the people as well who can take the program to that sort of level that you saw in the video earlier. So a little bit about our group then. This is the Aerospace Systems Research Group. The mission of the group in the general sense is to generate African academic talent in aerospace propulsion and to develop those commercializable rocket propulsion and related technologies. Our areas of specialization are hybrid rocket motor design. We do suborbital rocket design. Those are rockets that just go on a short suborbital hop into the high atmosphere. We are currently working on liquid rocket engine design, and we also have expertise in turbo machinery design, jet engines, in other words. And really our greatest, in a sense, our greatest achievement is the human capital development, the development of our students who become expert in rocket engineering. The group was formed in 2009, so we've been doing this now for about 11 or 12 years. We are driven by that new space philosophy that I talked about earlier, and we are passionate about delivering a commercial space launch capability for South Africa. That, in a nutshell, is why we do what we do. So we started small. This is a little bit more detail. We have grown this year. We are about 17 postgraduate students in the MSc and PhD programs. We have 4 full-time staff in ASREG, also, of course, mechanical engineers. And these flagship programs are Phoenix, which is our hybrid sounding rocket program, and the Sapphire liquid rocket engine program. So we are now one of the larger groups, or one of the largest aerospace research groups in South Africa. And as far as we know, because we have not yet discovered anyone else doing this, we are the only African group that is dedicated solely to rocket propulsion, these technologies. So we have along the way developed comprehensive know-how in suborbital hybrid propulsion, liquid rocket engines, launch vehicle design, launch operations, and those jet engine turbo machines. A little bit about our support. ASREG is supported by the Department of Science and Innovation, government departments, and through third stream income into the university. We have international collaboration. We also have strong industry linkages because this business is complex. Building rockets is a complex business, and you need to have suppliers that can deliver the manufacturing processes required to enable you to do the work that you do. We have a successful talent pipeline program to bring students through, including historically disadvantaged students. We have a coursework module in rocket propulsion that we contribute to the mechanical program. And we are doing all of this to build this foundation for the new space market in South Africa. Importantly, we have a sizable pool of highly skilled people. So it takes a lot of engineers to build these rockets, and we have had to grow our own timber in that respect. So the global small sat launch market is growing very quickly, as I said, and this is providing us with the incentive. That's a little bit about ASREG. Now I want to get into the geeky stuff and talk to you about how rockets are designed, because I think maybe you are interested in that process. So just a little bit of technical background. Rockets come in 3 basic types. These are chemical rockets. Chemical rockets are either solid rockets, or liquid rockets, or hybrids. So on the left of your screen, you will see this is a solid rocket. And basically, a rocket needs a fuel and an oxidizer in order to combust in the chamber, the combustion chamber. And then that high pressure, high energy gas is expelled through the nozzle at the back of the rocket. And that's what gives the rocket the momentum transfer to launch it into space. So in the case of a solid rocket, the propellants are mixed together into a solid paste. Well, it's a very viscous paste that is basically poured into a casing and set. And that propellant combination is like a very big firework. It's waiting to explode. And then when you eventually light it, the gases leave and expel through the base of the nozzle, as I said. So that's a solid rocket. The liquid rocket is a rocket that makes use of a liquid oxidizer and a liquid fuel. And those are kept separate from each other until they are combusted in the engine chamber at the back of the rocket. So what is the primary difference between these two? Well, solid rockets have a very specific kind of niche. They are very good at producing high levels of thrust to get rockets off the ground. They are quite compact, they're quite dense, so you can get a lot of energy in a fairly small rocket geometry. Disadvantage of a solid rocket is that they tend to be difficult. Well, they're almost impossible to throttle. They can be throttled, but it's very difficult to do that. and they can't really be stopped and started on a large scale. There is research into that going on, but it's very difficult to make that happen. So they're kind of like simple but powerful. That's a good way to kind of describe a solid rocket. Whereas a liquid rocket is much more complex to design, it's more complex to build because you've got to have plumbing, you've got to have valves and control valves and all sorts of difficult to implement systems to keep everything where it needs to be. But they are more flexible. You can throttle a liquid rocket, you can stop the engine, you can start it again, just like SpaceX does on those boosters. As you saw when the rocket booster was coming back down again, they started it up again. So that's a liquid rocket, and most commercial satellite launch vehicles are liquid rockets, although some of them have solid boosters strapped on to help them get off the ground. Then the third kind of rocket, which is one that we are very familiar with at UKZN, is the hybrid. And the hybrid consists of a liquid together with a solid. In most cases, the liquid is the oxidizer, which is stored in a tank, and the solid is cast into the combustion chamber as a grain. And the liquid oxidizer is then admitted into the chamber where it ignites and combusts. And that's why it's a hybrid, because it's a little bit of both of these rockets. Hybrids are really good for educational purposes because they are very safe. But in our case, we use fuel, which is basically just paraffin wax, so it's completely inert. And our oxidizer is nitrous oxide, which is also quite benign for the most part. So hybrids are very good for educational purposes because they are safe. They don't have great performance, but they are good for training because they also allow us to teach our students about the complexities of the plumbing that goes on in these liquid rockets. And we want to be in this liquid rocket space in terms of launch vehicles. Here's an example of some of these types. This is a sounding rocket. It's got a solid rocket on the back of it, solid rocket motor on the back. These are low altitude, well, they're high altitude, but suborbital rockets. And then, of course, the solid rocket boosters on the space shuttle. Most of you will remember the space shuttle. It's now been retired. Those two white elongated rockets that are strapped to the side of the main tank, those are solids. And they are also reusable. So when the shuttle takes off, after a short time, about a couple of minutes, it jettisons those and they fall back into the ocean, get collected with a boat, and then they get taken apart and they get reassembled for the next journey. So the shuttle is a very interesting vehicle because it also has liquid engines. So here we have an example of liquid engines. Those three engines at the back of the shuttle there, those are RS-25s. They are hydrogen-oxygen engines, and the hydrogen and the oxygen is stored inside this giant tank to which the vehicle is attached. The RS-25, generally considered to be one of the most advanced engines ever built, and of course reusable to an extent because you could fly the shuttle back and land it again. In practice, maybe not so reusable because they had to strip them down and pretty much rebuild them after most flights. So the shuttle was a reusable spacecraft, but it was not terribly practical. It used to take about 4 or 5 months for them to fix it up before they would send it on its way again. So it was reusable, but not terribly practical. And then, of course, an example of a hybrid rocket is our very own Phoenix, 1B Mark I, 1B Mark II. And inside this rocket, though you obviously can't see it, inside this part of the tank, there is nitrous oxide, and that fuel is at the base there, and the nitrous oxide is going through the tank, combusting with the fuel and producing the thrust. Interestingly enough, if you watch TV over the last couple of weeks and you saw Richard Branson going on a trip into a high atmosphere on his RSS Unity spacecraft, that Richard Branson spacecraft is also powered by a hybrid rocket. Right, so back to ASREG. ASREG is focused in 3 areas. We have our Phoenix hybrid rocket program, which I've just spoken about. You can see the Mark I rocket on the rail there in the picture. And then we have a liquid engine development program called SAPPHIRE, which stands for South African First Rocket Engine. And that is a that is a small sat launch vehicle class orbital engine. So that engine is designed to be placed on the back end, the base, the booster of the launch vehicle, 9 of them, and that will send the rocket into low Earth orbit together with an upper stage that has one of those engines. So that is in development at the moment. And then our third area of research, as I said earlier, is in turbo machine research. So these are rotating machines, pumps, fans, gas turbine engines. Right, let's talk about how you design a rocket, because I think you might be interested in this. So engineering design cycles are all pretty much the same. This is a kind of simplified version. And the cycle begins, in terms of the design part of the rocket, starts at the top here with specifying. So when we specify, we talk about what must the rocket do? How should it be configured? What are the mission parameters? In other words, what do we expect this rocket to actually do? How high do we want it to get? How far do we want it to go? What is its trajectory, speed, the duration of the flight? What kind of propellants are we going to use? What sort of preliminary vehicle architecture do we expect? Are we going to put the oxidizer tank on the top? Are we going to put the fuel tank on the top? Are we going to use a shuttle type architecture where you have the vehicle on the back of the tanks? There's all sorts of questions about the architecture of the rocket. And this is kind of decided at the specification stage using experience and so on. What kind of materials are we going to build it out of? And then are we going to recover it? What are we going to do in terms of avionics, the brain of the rocket? Where are we going to launch it from? How are we going to keep people safe? All of this comes into the specification stage. After that, we're going to do a preliminary design. So you can see there on the screen is a design of a rocket. That's a Phoenix Mark II hybrid rocket. And you can see that we've got the basic layout. This is a CAD drawing, so it's design of the vehicle that you would use before you start to manufacture it. We've got our oxidizer tank. We've got the motor on the back end there. This is a cutaway, so you can see into the motor, bits and pieces. And then on the sharp end, we've got the payload bay, we've got the recovery systems, and so on. So in the design phase, we haven't built anything yet. We're still designing for the mission. We're going to specify the motor size, the thrust, the impulse, and so on. When we have finished doing a basic preliminary design, we're then going to simulate the design and also the subsystems and the components on the rocket. We need to be sure, or as sure as possible, that the rocket is not going to fail. And to do that, we're going to test every single system. So here is an example. This is an injector bulkhead from a hybrid rocket. It's just a slice from the injector bulkhead. Obviously, it's not the whole thing. So when we simulate, this is a finite element analysis. And this is a cyclic symmetric section out of that bulkhead. And what the engineer will do is they will load that in the computer. Haven't built anything yet. Still in the computer. We'll apply loads. And then on the right of your screen, you see the output from the computer simulation. It's showing displacement of that bulkhead under these loads of various forces that are applied to the part. And we do this on just about every part. And we can also do this with fluid flow. And here's an example of a simulation, a computational fluid dynamics simulation showing what happens to the propellant when it goes through the chamber of one of those hybrid rockets. This is just a cold simulation looking at the way that the nitrous oxide flows through the chamber. And that's a CFD simulation. When we've finished simulating all the subcomponents and subsystems on the rocket, we then have to try and simulate the whole rocket itself. We need to know, where is this thing going to go if we launch it? Is it going to get to our apogee? Is it going to fulfill the mission parameters? And to make sure that it does that, we need some fancy software. And of course, this is complex stuff. In this particular case, the software that you see on the screen there, this is a screenshot from something called the Hybrid Rocket Performance Simulator, or HYROPS. This is a UKZN developed software program that allows us to test rocket flights, rocket trajectories. And what you see, in fact, is a kind of Monte Carlo analysis of where this rocket, which was launched in the right corner over here, it's flown on its trajectory, it's going to splash down somewhere over here, and these are contours which indicate the likelihood of it splashing down further away from that primary point. So I've got a little video and animation that I can show you out of Hyrox here. I want you to watch the rocket down here in the corner. This is the launch point in three-dimensional space. And up here, we've got the rocket itself. So the rocket is, you're going to see this spinning in real time, but you're going to see the trajectory emanating from the right-hand corner. And this is an actual simulation of what the rocket will do. So it gets to the top of its trajectory, it's got a recovery system, it's going to pop the parachute out, and then the whole system is going to float down and splash down in the ocean. So that's, by the way, that's not a cartoon, that's an actual physical simulation. This is a 6 degree of freedom simulator. So that's a pretty accurate analysis of what that rocket is going to do when it's actually launched. And we will repeat that analysis over and over again until we're confident that the vehicle is going to perform the way we expect it to. So that's the simulation phase in the design cycle. The next part of it is the evaluation. We're going to evaluate what we found. We're going to look at what all of this means. Does the vehicle meet all its mission requirements? Can the performance of these subsystems be improved? Is there a way to make the vehicle better? Can we manufacture it? No point in designing something that you can't manufacture. What effect does the design have on launch operations? And then issues of safety and so on. And lastly, well, in the cycle, you then iterate. And iterate means you do the whole thing all over again. So in this case, you would start again, you would look at your initial assumptions, and you would decide if there is any variation that you need to propose, and then you would iterate those variations through the design cycle. You would simulate again, track the design changes, conduct your regular design reviews until you can settle on a design, and of course focus on safety through the whole process. So that gives you a little bit of insight into how to design a rocket. Obviously, these are things that require a certain amount of experience. So it's always interesting to me when we put our team into a room and we say we want to do something, and we get the suggestions coming from the various engineers. Let's do it like this. No, what if we did it like that? Or I think you should do it like this. Remember when last time we tried that, it didn't work. So there's a lot of experience that goes into the process. When you've designed the rocket, you have to make it. So here are 3 rockets that we have built over the past few years. These are Phoenix series rockets. So at the top of the screen, you've got the Phoenix 1A, that was the first one we built. Then we have a Phoenix 1B Mark I and a Phoenix 1B Mark II. And you can see some of the specifications there. They're around about 5 meters long. They're about 80 kilograms or so in mass. And each of them produces, when they launch, they produce between 450 and about 600 or so kilograms of thrust. The propellants are wax, the fuel is wax, the oxidizer nitrous oxide. And you can see there the Mark I rocket was designed to go to about 10 kilometers in altitude. That's about the height of a commercial airliner like a Boeing 737 or so. And then the Mark II was designed to go quite a bit higher to 17 kilometers. So these are suborbital rockets, and you can see their speeds as well there. So back to this slide. If you look on the right of your screen, you'll see the motor detail there with the fuel grain and the post-combustion chamber, the nozzle, etc. So this is a cutaway section of that motor. And the gray that you see, the main part, the gray is the wax. And it's cast into that chamber as a solid, and it has a hole down the center, a port. And then when the nitrous oxide enters from the left, it flows down the port, combusts at the interface with the wax, and then the gases get expelled at high velocity through the nozzle. So if you want to make this grain, you have to employ a whole series of processes. And here are some photographs of real life processes. So we've got, this is what the grain looks like in the top photo, photo A. It's gray like that because it contains a certain amount of aluminium. We then have to line that grain. We have to attach pre and post combustion inserts, chamber inserts. We then have to line the grain so that it doesn't burn through the aluminium casing of the motor. And eventually we end up with this, with the liner looking like it does in photograph E. So it's quite an involved process to build just the grain of the rocket. And then of course you have to build the rest of the rocket as well. Now we get to the fun part, the testing part. I think this is the bit that most people are most interested in. This is where we look and see whether all the design and simulation has really paid off or not. So how to test rockets. So I've included here a quote from one of the astronauts on the Apollo 11 mission. This is Michael Collins, who wrote a very good biography called Carrying the Fire. And I recommend, if you haven't read it, to try and get a copy. And he was addressing this issue of rockets and testing them. And he said, you know, Apollo was the god who carried the fiery sun across the sky. But how would you carry fire? This is what he called his biography, Carrying Fire. And the answer is you carry it very carefully, with lots of planning and at considerable risk. It's a delicate cargo and it can spill. So testing rockets, flying rockets, is not an easy thing to do. And now I'm going to show you some video of some of the early tests that we did when we started out our program. So this video you're about to see, this is actually the very first rocket motor we ever fired at UKZN. And this was over a decade ago. And this is a tiny little hybrid rocket. It's never meant to fly. It's over-designed to stop any danger from it exploding or anything like that. And it was very interesting. It was a big day for us when this eventually fired. So it took us a while to get that motor to work. Here's another picture of some more tests. Similar size motor. Before I show you the next sequence here, the initial, that puff of brightly colored sparks that comes out of the front of the nozzle of the motor, that is the igniter. So getting a rocket motor or a rocket engine going is quite complicated because you have to supply enough heat, enough thermal energy to actually ignite the propellants. The propellants that we're using here are not what are called hypergolic. Hypergolic propellants don't need any additional help. They will just ignite on contact with each other. But with less energetic propellants, you have to start the process. So we have to employ igniters to do that. Well, those were the early days, and sooner or later you want to actually build a rocket. You don't want to just build the motor, you want to build the whole rocket. So this video shows the next step in the test procedure, and this is a static cold flow test. So once you've built your rocket, you want to be sure that the oxidizer goes through the system in the way that you expected and simulated it to do. So what we're going to show you here is the cold flow test of a EV2 motor. This is a much bigger motor, and this is actually the rocket that we launched earlier this year, one of the rockets. So all that's happening here is you're going to see the nitrous oxide come out of the motor. There's no flame. We haven't lit the motor because we want to see if the flow characteristics are as expected.
Sorry to cut you off, Professor Brook. Before you carry on, in terms of directing how do you think devices?
Okay, so that was a cold flow test. I'm going to ask you if you can just hold your questions, please, to the end of the presentation, and I'll address them there. Or you can leave a message in the chat box and we can talk about it there. So this is a cold flow test. Now, when you've completed a cold flow test, you then have to put the motor chamber onto the vehicle, onto the rocket, and actually fire it. And you'll notice here that we are holding the rocket down. Okay, now there's no danger of it flying here because there's no combustion, there's no thrust. But in the next video that I show you, we're going to now test the rocket motor itself in this same configuration. And this is where you really do have to make sure that you tie everything down because you don't want it departing the test stand. What I want you to listen to here as well, if you can hear it, listen to the sound that this PV2 motor makes. Listen to it. It makes a rather peculiar noise when it starts up, and see if you can pick that up on your side. So I don't know if you could hear that or not, but that was a what is called a screaming hybrid, right? I don't know if you picked up that sort of high-pitched whine that was audible shortly after ignition. And actually, that is not a good sign for a hybrid rocket, right? Typically, that is a form of instability. It's an acoustic instability inside the combustion chamber. And fortunately, in these PV2 and PV3 motors, it's not severe. So the motor is actually quite reliable. But if it gets out of hand, there have been cases where hybrid motors have blown themselves apart because of that instability. And speaking of that, things go well, and sometimes things don't go well at all. And this is the fun part. Well, it's not really fun, to be honest, but we engineers do like to watch failure videos because they tell us something about the engineering. And I'm going to show you some failure videos here, and I'm doing this because it's important to understand that rockets are very complex machines and they fail. And because they have so much energy stored in such a small space, when they go wrong, they tend to go wrong spectacularly. This is a YouTube video, and I'm going to show you some rockets going wrong. Here's another one.
One in 5 Titan rockets fail. Tough odds if you're a rocket man.
Tough odds indeed. I don't know if you're allowed to have a favorite rocket failure video. It might be a bit unseemly, but these are all unmanned, so maybe we can at least have a favorite. My favorite is the next one, and this is a Proton M vehicle, which is the Russian vehicle, and this failure occurred not too far in the distant past, actually. Okay, so the reason I showed you those videos for 2 reasons. One, because engineers learn from their mistakes, right? Testing is absolutely essential. Things can still go wrong. The second reason that I showed you that video is because it makes the next one seem like nothing, and this is one of our own failures, right? So I had an ulterior motive there. Here's a failure of a Phoenix rocket. Now, I'll talk to you about this. This failed shortly after launch because of a software fault in the program, controlling the main oxidizer valve. Oh, no, my apologies. This is actually the first rocket that we launched. It's not a dramatic failure, but I would like you to keep your eye closely on. It's a slow motion video. I want you to watch the back end of this rocket very carefully. This is Phoenix 1A. This was launched in 2014. It launched successfully, but there was a problem with it. And I want you to see if you can see what the problem is at the back end. This is slow-mo footage. Here we go. This is a high-speed camera. You can see quite a bit of instability in the plume there. Now I'll leave you to see if you can detect the problem. Yep, I hope you saw that. That was actually a fracture of the nozzle. The nozzle actually fractured on the back end of that rocket, and then the boat tail blew off. So fortunately, that was not destructive to the flight. It actually enabled the rocket. The rocket was still able to fly. There was another failure that we had a couple of years back, though, and I want to show you that one now as well.
Thanks a lot for your presentation, Mike Brook. My question was based upon the directing sky rockets. Is there someone inside who drives it, or you drive it using the sensing devices like a remote sort of?
No, then there's nobody on board any of the rockets we build. They're all unmanned and they are uncontrolled, so they're ballistic. So the small hybrid rockets that we build are ballistic. Right, I'm going to ask you if you can just hold your question to the end, and I will answer any questions at the end of the presentation, please. Right, so this is a hybrid rocket that failed shortly after launch. Ouch. I'm going to play that again.
It failed to go up.
Now, the interesting thing about this failure is that the really interesting thing is most people will see a video like this and it's terrible to see. And believe me, it was terrible to go through this. By the way, we were all sitting inside this blockhouse right next to the rocket, obviously in a safe condition. But it's very tough to watch something like this happen. But actually, this is a very interesting video because if you watch what happens when the rocket comes back down and impacts, all that you see there is the failure of the nitrous oxide tank. And that's just simply a pressurized tank failure. This rocket did not combust or detonate. It didn't explode. The tank failed under pressure, but there was no actual explosion. And this is a testimony to the relative safety of hybrid rockets. And it's one of the reasons that we use them in the university environment, because they are much safer to develop. If this had been a liquid vehicle falling back onto the pad, it would have resulted in a major conflagration. As it turns out, there was very little damage to any of the structure. Our launch gantry just required fairly minor repairs. So this is an example of why hybrid rockets are a really good idea for these sorts of applications. Right, I'm going to go back to the presentation and try and wrap things up now.
So skyrockets have a high number of risks compared to the airplane.
There are lots of risks associated with rockets, for sure. And the risks are higher for rockets than commercial aircraft. That is true, although rockets are increasingly safe in terms of their reliability. All right, so we'll carry on. And I've got a quote here from Elon Musk, and he says, if things aren't failing, you are not innovating enough. And that's a very interesting quote. Obviously, we're not championing the idea of failure, but you learn a lot in engineering from failing, and you can learn a lot from these tests. So yeah, his motto is fail fast and fail forward, right? So you test a lot, you test repeatedly, and that's the way that these things go. So you learn a lot from that process. So I want to move then on to the Phoenix campaign, which was our launch campaign that happened earlier this year, 2021. I won't go through this in detail because we're a little bit behind on the schedule, but we had many aims. We aimed to launch 2 rockets, Phoenix Mark II and a Mark IIR and a Phoenix Mark I rocket from Overberg Test Range. There was lots going on in terms of the test plan. Overberg Test Range, Denel Overberg Test Range, is down on the Western Cape. It is a very professionally run test facility for aerospace engineering. And it is located just to the east of Cape Agulhas. And the flight paths that we use here are for sounding rockets, either inland if it's a short distance, or out over the Indian Ocean. Right, so I'm going to show you a brief part of the video that we produced in the wake of our test campaign, and I will show you that shortly. This will give you a sense of the test and the preparation that goes into a launch.
So for detecting the other planets, we use the sky rocket. So there is another equipment we use for detecting the other planets. Also is the NASA and other planets. Ignition.
Right, I will wrap things up now. Get back to the presentation. So we got some good results from that flight test of the two Phoenix rockets. You can see there some of the key numbers, and on the right of the screen, some of the camera shots that we managed to get from the camera that was placed on the front end of the Mark II-R vehicle. And you can see some nice dark sky above there that got to an altitude of about 18 kilometers. So just to wrap things up, the message from today is we do this research because we are in the middle of a new space race, and rocket engineering is once again in high demand, a bit like it was all those years ago in the first space race. So it's very demanding to design, build, and test rockets, but it is tremendously rewarding experience as well. Rocket engineering draws on all of these major engineering disciplines. It's got mechanical engineering, it's got chemical engineering, got electrical, electronic engineering. There's even a bit of civil engineering in there as well. So it's got a little bit of everything. Society is relying more and more on these satellites that are going into space. Your GPS function on your cell phone, or your DSTV for watching TV is, all of this relies on satellites, and the only way to get a satellite into orbit at this point is using a rocket. So for those of you who are out there who are considering your future study opportunities, if you are strong in mathematics and physical science, then I invite you to come and fly rockets with us at UKZN. And then just to acknowledge the support that we get from the Department of Science and Innovation and our industry's partners, RDM, DIY Electronics, and our various other partners as well. And then lastly, just to dedicate this presentation to all our students. None of this would be possible without the students who have formed such an integral part of ASREG over the past 12 years. And you know, we find the program tremendously helpful. It's inspirational. We have mechanical students coming all the way through the undergraduate program. They get into the postgraduate program. They do research. They make a contribution. They come and fly these rockets with us. And all of the work that you've seen here today is their work. So this is very much the presentation dedicated to them. And on that note, Sally, I will wrap things up. Tanya, I think there may be just a few minutes for questions. If anybody has any questions, feel free to go ahead and ask. Thanks very much.
Thank you so much, Mike, for this awesome presentation and a very deep insight into the UKZN rocket science thing. So I'll next time I'm going to go outside, I'll just watch for your rocket in the bush, okay? There are a few questions coming up, and I'll just pick some randomly, which I think are quite good. There is a question from Baron Duplessis. Is South Africa now looking at launch capabilities? Can we compete with this high-level engineering environment? Who would fund such projects? Mike, did you get the question?
Yes, I did. Okay. Thanks for that question. So I think that there is always interest in the potential of expanding the advanced manufacturing base in South Africa. I think that the government is probably interested in rocketry if that it can be made as a viable business case. So the question is more about whether there's a business case, and the question there is, can we capture enough of that, $16 or $18 billion US market that allows us to create a program that can sustain itself. I believe that it is possible for us to do that, but whether the government is going to come to the party on that remains to be seen. But there is a discussion going on in the background, I can say that much.
There's also, I think that question ties quite nicely into what you were just saying from Arti Pandai. Jeff Bezos' recently sparked a bit of controversy where the public feels money should rather be spent on social issues like hunger and poverty. What are your thoughts as leading researcher on the continent about this strong view? Do you feel your work will threaten by dwindling funds in the future?
Yeah, so what we have to appreciate about space is that it's not something that happens over there done by people who take money from other causes and waste it. Space is already part of our lives. It's part of your life already. If you don't believe me, then put your cell phone away and don't use it for a week, because your cell phone relies in many respects on satellite technology. Your GPS system is satellite-based. When you sit down to watch DSTV, it's satellite-based. All that fantastic footage coming to us from the Olympic Games is coming to us by satellite. And then there are even other areas where people are not aware. The camera in your cell phone is probably a CMOS camera. CMOS cameras were brought to market effectively by work done at the Jet Propulsion Lab by NASA. So, even stuff that doesn't seem like it comes from space is an indirect result of the space effort. A lot of the work being done on the International Space Station right now is looking at the way to build molecules in a weightless environment. You couldn't do that research if you didn't have rockets to get the space station into space. So I would say that what we have is a need for education. People need to understand that rocketry is not something that is nice to have. It's an integrated part of our lives. It already is an integrated part of our lives. So I think that when we talk about these arguments, should we spend more on poverty alleviation, etc., we have to remember that we live in a holistic sense, and there's a lot of what goes into society that comes from these various science programs.
Thank you. And there's an interesting question from Kondo. When building the rockets, how do you ensure the safety of the environment? So do material undergo some sort of test to ensure that there is no negative impact to the environment?
Yeah, whenever we launch a rocket or do any kind of test, we always go through quite an exhaustive risk assessment. And obviously, perhaps not so obvious, but we certainly don't do these tests in areas where we don't just decide we're going to run a rocket test and then we start it up. Most of the rocket tests that we do occur in licensed facilities that belong to our industrial partners. Those facilities have been very, very carefully planned. There have been impact assessments. We look at what we do very carefully. None of the rockets that we build or test contain toxic materials. There are some very toxic propellants out there, very toxic, but we're not using those. So I think it's important. Overberg Test Range is actually quite an interesting case study because it's a test facility. You saw it there in the video that I played earlier. It's also a reserve, a conservancy, and it's quite amazing to drive along the roads inside the test facility and to see bontebok and ostrich running alongside the road. Those animals would not be safe if it was not for the facility. So it's a mistake to think that this kind of high-tech environment or this kind of high-tech activity cannot coexist very peaceably with conservation efforts. It's already happening and quite successfully.
Thanks. And Lorik, if you quickly unmute yourself, you can ask one question, not two questions, just one question. So quickly ask your question.
All right, thanks for that. Hi, Prof. Brooks. My name is Lorik. I just wanted to find out, you mentioned that the hybrid motors that you have been working on are, they're obviously relatively low performance. Has there been scope, or is there scope in the future for research into performance improvements? I'm thinking specifically things like cryogenic storage of particularly the oxidizer in this case, to increase the density and those sorts of things.
Yeah, thanks, Lorik. There is a lot of work going into hybrids. As I mentioned earlier, the RSS Unity, the Virgin Galactic spacecraft that you would have seen Richard Branson going to the high atmosphere recently, that has a hybrid motor on it. And hybrid motors are, the problem with hybrids, if you wanted to be very critical of them, some people say that they combine the worst of the liquids and the worst of the solids because they don't have a particularly high specific impulse. So, their performance is not great, but they do have niche applications. And there has been some talk of the application of hybrids in ascent vehicles from planetary exploration missions. So if you go to Mars and you want to get off the surface of Mars, maybe you could use a hybrid motor there because it sort of fits the mission profile. So there's always rocketry is fascinating because it's all about niche. It's all about finding that little niche where that particular configuration just happens to work. But to answer your question directly, there's a lot of work going into hybrid rockets. The AIAA in the US has a special group working on rockets, on hybrids, a special interest group, a technical committee working on them. And yeah, there's a lot of work going into hybrids. I think there's even a booster hybrid under development, I think by the Chinese. It's a Chinese company, I think. So there's lots of work going on in all sorts of rocket applications.
Thank you so much. Unfortunately, we won't be able to answer all the questions. So Mike, if you just want to share your email address in the chat, then people can directly ask you a question. And you probably are quite happy to answer them, if I'm correct.
Yeah, sure. Tanya, I can go another 10 minutes on the questions if people want to do that. It's quicker to answer, but I think I can do another 10 minutes if anyone wants to ask a few more questions.
Okay, so do you want me to read out, or shall the guys?
Yeah, you can read out a question if you want. Just go for it.
Okay, so from Victor Dubé, how far does one need to be away from the launch site? Because in the video that showed the protons-fed launch, it had fallen quite a bit of the distance away from where it was launched. So I'm pretty sure standing right next to a launch pad is not a good idea.
That's a good, yeah, it's a good question. So when you design a rocket, you put a certain amount of propellant into the rocket, and that propellant has what is called a TNT equivalency. So everyone knows what TNT is. It's an explosive. It's kind of like the baseline. So 1 kilogram of TNT is kind of like the baseline unit. And then you have TNT equivalencies. So every rocket has got a TNT equivalency, which defines how dangerous it is to be near it, right? So if you look at the very big commercial rockets, like the ones that launch out of Cape Canaveral in the US, there is no human settlement closer than 10 miles away from the launch pad at Cape Canaveral. So you will never get closer than 10 miles. And all of these commercial rockets have got what we call destruct systems on them. So there's a controller, and if the rocket starts to go off course, then the controller will push a button and the rocket will explode. Interestingly enough, the Russians do things a little bit differently, and that Proton launch that you saw, the failure that you saw earlier, that was quite interesting. That rocket got quite a way away from its pad. So, and by the way, that rocket was also using very, very nasty propellants. That rocket, I believe, uses the combination of nitrogen. Let me just get this right. No, it's nitrogen tetroxide and hydrazine, I believe, and which accounts for the very bright red color that you see when it explodes on the ground. You don't want to be anywhere near hydrazine. It's actually carcinogenic. So yeah, you've got to be really careful you don't get near these things. But the safety standards are very high, and you will not be allowed anywhere near a rocket launch. But obviously, smaller rockets, you don't have to be so far away because the explosive risk is lower.
And I know that Gregory is waiting for his question, so he says, pretty please. Is there any time frame for Sapphire engine first test fire?
Yes, there is. I can't answer that, unfortunately, but yes, we are on track.
Okay, right. Let me just find something else. Okay, so with regards to the development of the Sapphire engine for use with potential future South African or private launch vehicle, what is an okay, that's okay. In time frame, we're not going to talk about this. Additionally, when the point of orbital launch capability for Sapphire is reached, will launches be conducted from South African soil? If so, won't we be limited in payload type by the fairly high orbital inclination angle of launch from such a low altitude? Yo, that was quite a bit of a question.
Yeah, so from South Africa, realistically speaking, the only launch types of orbits that we can get into from here with the vehicles that we're proposing are polar orbits. But polar orbits are very popular, and there's a big need for them. So the vehicle launched from South Africa would head south, pretty much from Overberg Test Range, and we very definitely would aim to launch from South Africa if we could get that far, because in the launch business, you really want to have the whole thing. You want to own the whole thing. You want to build the rocket. You want to build the engines. You want to build the second and first stages. You want to build the satellites if you can, and you want to own the launch facility, because then you can offer a complete service. So the ultimate model is to launch South African built rockets with customer satellites from Overberg Test Range. That's the kind of intention.
Okay, thank you, Mike. Thank you very, very much for this fantastic presentation. And I just want to announce 2 other exciting talks that are coming up tomorrow. Please join us for Ms. Nkizo Moso, a very bright young female South African who's going to talk about mysterious Marion Island and developing and testing radio astronomical equipment in the cold. And be aware, you take your winter woolly and so on. And on Thursday, we have Professor Andrew Green, who's going to lift back the waters, adventures in the Southern African marine geology. So instead of going up, he goes down. So please, ladies and gentlemen, support us. And thanks again, Mike. And if we can just unmute yourself and give him a big round of applause, if we can try this.
Thanks, everyone.
Everybody's now, yes, thank you.